Welcome to the very first lecture of our course. We're going to jump right in. Now, this lecture material corresponds to different chapters in our textbook, which is Conceptual Physical Science, 6th edition by Hewitt, Suchoki, and Hewitt. I probably mispronounced one of those names, but anyway, we're going to just jump right in and get started. The first chapter is titled Patterns of Motion and Equilibrium, and we're going to be looking at how things move and why things move. Now, one of the first people to ever really systematically think about these issues of motion and study them was a guy you've probably heard of before. His name was Aristotle. You can see a picture here of a statue of him from the ancient world. And Aristotle actually wrote a book called Physics. The word physics is Greek for nature, so it was Aristotle's attempt to describe nature, to describe our universe, and he very systematically looked at ideas about force and motion. And I'll jump to the end here. Aristotle's views on motion were wrong. In fact, much of what Aristotle wrote about physics was just simply wrong. Physicists sometimes kind of give Aristotle a little bit of grief about this, but there is maybe some perspective worth thinking about. When I teach the in-person version of this class, I very often will ask my students if they've ever heard of Aristotle, if they know who he was. And almost always, at least some of the students have heard of him, and somebody will raise their hand, and I'll ask, what is he famous for? And somebody will inevitably tell me philosophy. That's what people remember him for. You know, the ancient Greek philosophers, the three biggest were Aristotle, Plato, and Socrates. Most people are familiar with those names and know that they're associated with philosophy. Here's an interesting thing, though. If you ever took a course in biology, you might have learned that Aristotle is also considered the father of biology. He's the person who invented biology as a modern science. He's the one that taught us how to systematically study biology. And he's considered the father of biology because of that. What's crazy is that most people don't know that about him. His work in philosophy was so important. The fact that he's considered the father of one of the major branches of science is kind of a footnote in his career. So yes, he got a lot wrong about physics, but I think we can cut him some slack maybe, because he was a brilliant scientist in his own way, and of course one of the greatest philosophers of all time. Now, in terms of motion, Aristotle imagined that there were two types of motion that he called violent motion and natural motion. And natural motion was that things tend to seek their place. This was his idea. And it's not a correct idea. Let me reemphasize this. This is wrong, but this is what he said. He said that things tend to seek their place. So smoke from a fire tends to rise because it wants to go up to the heavens, and heavy stones drop to the ground because stones want to be on the ground. And he also described what he called violent motion. And his idea of violent motion was that you need a force to keep things moving. So here I've drawn a little arrow. Imagine an arrow shot from a bow traveling through the air. What Aristotle imagined was that the wind would rush past the arrow as it flew through the air and somehow loop back and continue to push it forward. In other words, to keep that arrow going, there had to be something pushing it forward. It turns out that's not true, and we're going to see why that's not true in a little bit. One of the next big names in the study of motion is a guy named Galileo Galilei. And we generally just call him Galileo. Here you can see how to spell it. Galileo, obviously his picture's over here on the right. He was able to fix a lot of what Aristotle got wrong about motion. And the way he did it was he used experiment. Experiment is the key to doing science. Now again, before we get too much into the Aristotle bashing camp, Galileo had something that Aristotle didn't have. He had a clock. Now, by today's standards, his clock was a terrible clock. It was literally a bag of water with a valve on it that would let water drip out at a steady rate. Drip, drip, drip. But he could use that to keep time. He could count the number of drips. If you want to study how things move, you need to know how long it takes to move from some point to some other point. And by having a clock, you can put a number to that. You can compare this motion to that motion in a very systematic way. That was something that Galileo had available that Aristotle didn't. All Aristotle could do was think about things and use logic. And the things that Aristotle said weren't crazy, they just weren't correct. But Galileo was able to do experiment. He was able to test his hypotheses and show that they were correct. One of the things that Aristotle said was that if I have two balls of the same size and I drop them from the same height, if one of them weighs more than the other, gravity is pulling it down harder, so it should hit the ground first. Because it's heavier, it should hit the ground first. That's not a crazy thing to think. It's a very straightforward idea. It just happens to be wrong. Two cannonballs, one made out of something that's very heavy and one made out of something that's very light. If you drop them from the same height at the same time, they're actually going to fall together and they'll hit the ground at the same time. Legend says that Galileo actually performed this experiment. He went to the top of the Leaning Tower of Pisa. If you've ever heard of that before, it's a very famous tower in Italy, which at the time was one of the tallest buildings available. And so it's said that Galileo went to the top and he dropped two different weighted balls at the same time, and he had someone on the ground to watch. And what they found was that they hit the ground at the same time, just as he knew that they would, because he had done many, many other experiments with motion in his lab, and he knew that that was going to be the case. So Aristotle said the heavier ball would hit first, but experiment said the two balls will hit the ground at the same time. And guess which one was right? The one that's verified by experiment. Now, over on the right, I have another figure from your textbook with a cannon shooting a cannonball, and it asks the question, does a force keep the cannonball moving after it leaves the cannon? What do you think? Yes or no? Is a force necessary to keep that ball moving through the air or not? Well, this is just like the example I did on the previous slide with the arrow. You don't need some force pushing the cannonball forward. Once it leaves the barrel of the cannon, it's moving under its own momentum. It just will keep going until it hits something, or until air resistance slows it down, or until it falls to the ground. But there isn't a need for something behind the cannonball to keep pushing it forward. Once it leaves the cannon, it's going forward under its own momentum. It doesn't need something else to keep pushing it. Now, this idea that something can keep moving forward without being pushed is very unintuitive. It's maybe if you didn't know any better, you might think that Aristotle was right. Aristotle's idea isn't crazy. To keep something moving forward, you got to keep pushing on it. It sounds like it could be true. It's just not true. So this is how Galileo figured it out. He did these experiments where he would roll balls down hills and roll balls up hills. And so you can imagine that if he had a ball here and he let it roll down the hill, it's going to go forward a little bit and it's going to come up. And what he found was that it would come up to exactly the same height that it started with. And this was true even if it went a further distance. Now, that's a little bit of a fib there. It didn't go exactly to the same height, but it got really, really close. And what he found was that if he polished the ground to make it smoother, i.e. to make it have less friction, it would get closer and closer to that top position the smoother the ground was. And so what he recognized was when he let it go and it didn't get exactly back up to the top, it's because there was some friction with the ground slowing it down. But if he imagined, and he was right, if somehow he could completely eliminate friction, it would go exactly to the top no matter how far it went along the ground. And so Galileo imagined, well, what if I didn't have this second hill going up? What if I let it go and have it go straight? If there were no friction to slow the ball down, the ball would just keep rolling forever. It wouldn't need someone to continually push it forward. It would just keep going. Again, that's not a very intuitive response. That's maybe not something that you would guess, but that's the way our reality is in this universe. Once you get something going, it doesn't take a force to keep it going. Now, if there is another force, that other force could speed it up or slow it down or change how it's moving. But once it's moving, absent any forces, it's just going to keep moving how it's moving. So we've talked about force, but we haven't really said exactly what a force is. And part of that's because most people know what a force is. And the definition for it's actually pretty simple. A force is simply a push or a pull. Now, there are actually two different kinds of forces that we talk about. We talk about contact forces. Here I've drawn, you can imagine a wall and somebody is pushing on the wall with the force. Maybe their hands are pushing against the wall. The hands are in contact with the wall, so that is a contact force. Another example is the force of gravity. Now you can imagine we have the moon here and the earth, and of course this picture is not drawn to scale, but we know that the moon goes around the earth, and it does so because gravity holds it close to the earth. The force of gravity between the moon and the earth is an example of what we call an action at a distance force. And so there doesn't have to be contact with gravity. It can act over a distance. Now, before we go on, I want to mention that most physical quantities have something that we call units. And units let you determine how much of a particular quantity something is. So, for example, if I wanted to know how far apart you and I were, you would tell me some distance. Now, if you tell me that we're 10 feet apart, I know how far apart we are because I know how much a foot is, how much feet are. If, on the other hand, you tell me that we're 10 miles apart, maybe we're in different towns, that's a distance again that I'm familiar with. I know basically how far away a mile is. And so feet and miles are examples of units. They give you the amount of stuff. And so I can say 10 is the amount, but 10 what? 10 feet. Now I know what I'm talking about. 10 miles. Now I know what I'm talking about. So the feet and the miles, those are examples of units. Now, when we're talking about forces, and hey, what's a force again? What's the definition of force? It's a push or a pull. So how much am I pushing or pulling? That's what the units tell me. And so the standards of units, just like we could talk about feet and miles, or we could talk about meters or kilometers, well, the two usual ways to talk about force are either the pound or the Newton. Now, the pound is one that you're probably very familiar with because that's what we use in the United States. And Newton really is only used by scientists, but that's the official unit of force in the metric system. And so we're going to use Newtons usually when we're talking about forces because scientists use the metric system. Now, if I tell you something weighs 50 pounds, you kind of have a sense of what that means. But if I tell you something weighs 50 newtons, most people have no idea what 50 newtons means. So just FYI, a newton is about a quarter of a pound. Not quite, but pretty close to being about a quarter of a pound. If you have ever heard the story about Isaac Newton had an apple fall on his head, a good-sized apple weighs about a newton. So if you imagine a bag with 50 apples in it, that'd give you a good sense about how much 50 newtons weighs. Or you could simply divide by 4 and get kind of a guesstimate that way. Now, when we want to talk about forces, there are 3 very important ideas that we need to understand. And you need to learn these definitions. You need to know what these terms mean because we're going to refer to them over and over again. And if you don't know what they mean, you'll be lost. And I'd like to take a moment here to just make a suggestion because in this class we are going to have a lot of definitions. and you kind of need to know the definitions. One of the things that I often suggest to my students is using flashcards. Flashcards are a great way to learn definitions. They worked for you in third grade and they will work for you now. Now, you can actually go to the store and buy a bunch of index cards and make your own flashcards with pen or pencil. But if you have a smartphone, you may find that there are lots of free or very inexpensive flashcard apps that are quite nice. And so you can put these flashcards on your phone and you always have them with you. So if you're checking out at the line at Walmart, you can whip out your phone and, run through some definitions. Also, what's great about these smartphone apps is that they tend to show you the words that you don't know as well more often. So instead of rehearsing words you already know, it really focuses on the words that you're struggling with. And so it's much more efficient. I really recommend you guys look into possibly getting a flashcard app on your phone and using it to help you with this class and all of your classes, because it's just a great tool to have. Anyway, let's get back to the slide. So the three definitions we're going to talk about are called inertia. Inertia is the resistance of a body to a force. Now, we're going to talk about this more later on, but this is a very important idea. If you push on an object, it's going to change its motion, but how much it changes its motion depends on how much inertia it has. And what we call the amount of inertia that a body has, we define that as its mass. And so this is the definition of mass. We say that mass is the amount of inertia in a body. In other words, it's the amount of resistance that a body will give back to a force. And as a general rule, more matter means more inertia. So if I've got 1 bar of gold, it's going to have a certain amount of mass, a certain amount of inertia. If I have a second identical bar of gold, I've doubled the mass. I've got more matter, more mass, more inertia. And then finally, something that people very often mix up with mass is the idea of weight. And we're going to talk about these things in more detail, but just know that weight is a force. Mass is a measure of inertia. Weight is a measure of force. Specifically, it's the force of gravity acting on a mass. That's what weight is. Now, the standard unit of mass, and again, we're talking about the metric system because that's what we use in science, and you all learned about the metric system in grade school, I'm sure. And so, just FYI, if you're talking about 1 kilogram of mass, that has a weight of about 10 newtons. The exact amount is 9.81 newtons, but usually we'll round that up to 10 in this class because 10 is just an easier number to work with. And just FYI, a kilogram has a weight of about 2.2 pounds. So 10 newtons is about 2.2 pounds.